Now let's look at one of the key formulas in option pricing, the Black-Scholes formula, which has a lot of applications in the option world and which has used the concept of the standard normal variable to a large extent. And probably the most widely used formula when we are looking at pricing either the European call option or European put options. So this formula becomes more and more logically applicable, and the major assumption which is driving this particular formula is the prices of the underlying asset. They follow a log normal distribution. The prices of the underlying asset, they follow a log normal distribution, which means if I am looking at let's say two time periods T1 and T2, and let's say I am observing that the price at T1 is S of T1 of the asset and price at time T2 is S of T2. Now what we are saying is this particular in this particular scenario, S of T2 divided by S of T1 is a variable. If I am defining probably X as S of T2 by S of T1, this is going to follow a log normal distribution. This is going to follow a log normal distribution, and the parameters of this log normal distribution are going to be mu minus q minus sigma squared by 2, and because we are talking of two time periods T2 minus T2 and T1, so the parameter is mu minus q minus sigma squared by 2 T2 minus T1 and sigma squared times T2 minus T1. What that does mean is if I am taking the logarithm of S of T2 by S of T1, this should follow a normal distribution with the parameters. This should follow a log normal distribution because in case of a log normal, the logarithm of it will follow a normal distribution. So what we generally see is this, I can write it as mu minus q minus sigma squared by 2 into T2 minus T1 plus sigma into square root of T2 minus T1 z. Because if you remember, any normal variable, I can write it in the form of standard normal variable using mu plus sigma z. Now mu in that case is this one, and sigma squared in the case is this one. So sigma will become sigma times square root of T2 minus T1. So I can very well write the expression for log S of T2 divided by S of T1 in this particular form. So where Z is the standard normal variable and mu is called as the drift, and sigma is called as the volatility of the price of the underlying asset, and probably here we could look at the drift is nothing but the expected returns or the expected value of the returns of the underlying asset and this represents the standard deviation of the returns of the underlying asset. And Q is like a continuous dividend that is typically paid by the asset, and of course in some cases when the asset pays no dividend, I can very well take Q as 0. So once we know that these are the scenarios, here whenever I am using a Black-Scholes formula to typically do the pricing of the option, we are using one, the spot price of the security of the asset, which is the current price. Then I am looking at the strike price of the option, the price at which the future buying or selling of the underlying is going to happen. We are looking at the time to maturity of the option. Generally we denote it as T minus T, where T is the maturity period and T is the point on which we are doing the valuation. So the time to maturity, let's say measured in years. Then I am looking at R, which is the risk-free rate, and as a part of this Black-Scholes formula, this particular risk-free rate is assumed to be constant over the life of the option. So if I am saying my option is a 3-monthly option, then over the entire 3-month period I am assuming that the risk-free rate of interest is going to be constant. Then the sigma, which we are calling as the volatility of the asset returns, even here also the volatility which is coming out with respect to the standard deviation of the returns of the asset, again this is assumed to be constant over the period. And finally I am looking at Q, which is the rate of dividend, the rate of dividend declared on the underlying asset on which is paid on a continuous basis. So these are some of the important aspects that go as a part of the Black-Scholes formula. The main underlying assumption is the stock prices follow a log normal distribution, or the asset prices follow a log normal distribution. And in that we are seeing this particular ratio ST2 divided by ST1, that is the one which is log normal, and the parameters of that are going to be this. So the logarithm of this is going to be a normal random variable, and I can express that normal random variable in the form of a standard normal variable using mu plus sigma z kind of a mechanism. So that is what is going to come out with this process. And using this, we can very well go ahead in terms of finding out the price of a call option, European call option, or a price of a European put option. Just giving the formulas for the same, the price of a European call option goes like whatever is the spot price, adjust it with the present value of the dividend, right? So when I am dividing it by e power q t minus t, that is what giving me the present value of the dividend. This I multiply it with the cumulative distribution of a standard normal variable d1 minus the strike price, the present value of the strike price times ND2, wherein I am talking about D1 and D2 as log S by X. We are talking about a standard, the logarithm of it follows a normal distribution. So that's where we are taking log S by X, and I'm taking it as r minus q plus sigma squared by 2 into t minus t divided by sigma root t. This is what is coming out as d1, and d2 comes out as d1 minus sigma root t minus t, which actually works out as log s by x plus r minus q minus sigma squared by 2 into t minus t divided by sigma root t minus t. Now, whatever we have got nd1 or nd2, it's nothing but 1 by root 2 pi integral minus infinite to t1 e power minus x squared by 2 dx. So, which is nothing but a standard normal variable coming up. And in case this particular stock is paying no dividend, probably here my value of the call option becomes S times ND1 minus K e power minus R T minus T times ND2. That's the small modification that comes. And even in D1 I get it as log S by X plus R plus sigma squared by 2 into T minus T divided by sigma root t minus t. I'll not have the q term at all. So that is the case in case the particular asset doesn't pay any kind of a dividend, right? So these are some of the important relationships, and now I know that the price of a call option is something I can very well work out to find the price of the European put option as well, because we have right now worked out that the price of the European call option is S into e power minus q times t minus t in nd1 minus k e power, or probably x e power minus r t minus t nd2. Now we know that the put call parity relationship is the difference between call and a put should be equal to the spot price minus the present value of the strike price. Now here I am talking about the stock price with a dividend, so it should be e power minus q t minus t minus k e power minus r t minus t. So from here we can talk about the price of put option. So P should be price of a call. What is the price of a call? C e power minus q t minus t and d1 minus x. Okay, probably for strike price either I can use x or k. X e power minus r t minus t and d2 minus s, because p if I want c minus s plus x e power minus rt. So I'll write it as c e power s e power minus q t minus t plus x e power minus r t minus t. This is the expression. So if I am taking the commonalities out, so it comes out as s e power minus q t minus t times nd1 minus 1 minus, if I am taking x e power minus r t minus t, then it is coming out as nd2 minus 1. So it is probably working out as we have seen earlier 1 minus nd1 is nothing but n of minus d1. So probably from here I can very well choose the mechanism, right? If I'm looking at taking out a minus out across all, it is coming out like x e power minus r t minus t. This comes out as 1 minus nd2 becomes n of minus d2 minus s e power minus q times t minus t 1 minus nd1 becoming n of minus d1. So this is what will become the price of a European put option using the call put parity relationship and the price of a European call option. So this is what is a pricing. This is what is one of the applications of the standard normal variable or a log normal variable whose logarithm follows a kind of a normal kind of a distribution, and how this Black-Scholes formula is typically used. We will see at a later stage the derivation part of it, but majorly it is using the stochastic calculus Ito's lemma to typically derive this Black-Scholes formula. But one of the important things we need to understand is the underlying distribution that is driving this Black-Scholes formula. Alright. Now let's look at how we can derive the Black-Scholes formula for computing the price of either a European call option or a European put option using the risk neutral valuation model. Whenever I say risk neutral, what is that? We are looking at, whenever we are talking about a risk neutral pricing or risk neutral valuation, we are looking at discounting the expected future payoffs. Expected future payoffs that are going to come on maturity. That is what when I am discounting them to the present value, that is what we call as a risk neutral valuation. And here, especially with respect to this option pricing, we go under the assumption that the asset prices follow a log normal distribution, which means the logarithm of the asset prices is going to follow the normal distribution, which means if at all I want to look at the value of the option, we are looking at, okay, what is the expected value or expected payoff at time t, and I am taking the discounting of it, so I am doing it e to the power of minus rt. So this is what will give me the value of the option based on a risk neutral valuation model. And we have already established the typical fact, the log normal model for the asset prices. We have established the equation saying log S2 by S1, which is the logarithms of the returns. We have already established that it can be modeled in the form of mu minus q minus sigma squared by 2 into t, which is the difference in the time periods between S2 and S1, plus sigma times the square root of T2 minus T1 times normal standard normal variable Z. Now the same application is what I am going to use even now under the assumption that mu I am taking it as some r, and T2 minus T1 I'll take it as T minus 0, which means T2 I take as T, T1 I take as 0, which means T period to maturity. Whatever I'm talking of, I have T period to maturity. So I'm taking it as 0, T1 I'm taking as 0, T2 I'm taking as capital T, which means the same formula logarithm S2 by S1 will become R minus Q minus sigma squared by 2 times T plus sigma root T times Z. So that is the kind of an equation I am going to use. And here also, because I have made T2 and T1 already, so I can call this as ST divided by S0. So that is the first equation I am going to get, log ST divided by S0. I'll make it as R minus Q minus sigma squared by 2 into T plus sigma root T times Z. So from here I can simplify. I'll take out the log. ST by S naught will become e to the power of R minus Q minus sigma squared by 2 times T plus sigma root T times Z. So from there I get ST is coming out as S0 times e to the power R minus Q minus sigma squared by 2 times T plus sigma root T times Z. So this is what is an expression for ST. So now let's say I want to do the price determination for a European call option. Now what is the payoff? See, if I am going with a risk neutral pricing model, the payoff for a European call option is typically the maximum. First let me look at the payoff. Maximum of ST minus K comma 0. This is what is the payoff, and I'll take the present value of that. That is what should be the price, right? The expected value of the maximum of ST minus K comma 0 times e to the power of minus RT. That is the price of the call option. The same way, probably if I am looking at the price of the put option, e to the power of minus RT times the expected value of maximum of K minus ST comma 0. So now what we will try to see is, first let me work it out for the call option. So I need to know maximum of ST minus K comma 0, which generally occurs if, so this I can very well write it as the value is equal to ST minus K if ST is greater than K, and it is equal to 0 in the other cases, correct? So what do we mean by ST greater than K? Probably I'll try to write it. ST greater than K, I can very well write it in this particular form, right? So when I am saying ST is greater than K, it is as good as, so let me go to the next step. I am writing ST is greater than K. What does that mean? I'll take it from here. ST is nothing but S naught into this. So that should be greater than K, right? So if I'm looking at that, S naught times e to the power of R minus Q minus sigma squared by 2 times T plus sigma root T Z. This entire thing should be greater than or equal to K. Again, a simplification now. E to the power of R minus Q minus sigma squared by 2 into T plus sigma root T Z is greater than or equal to K by S naught. And probably again, if I am taking out the E power, R minus Q minus sigma squared by 2 times T plus sigma root T times Z is greater than or equal to log K by S naught. Now from here I am establishing for z. Z greater than or equal to log k by s naught minus r minus q minus sigma squared by 2 times t divided by sigma root t. So the other way I can write z greater than or equal to, I take out the minus out, I say log s naught by k plus r minus q minus sigma squared by 2 times t divided by sigma root t, which is actually becoming z greater than or equal to minus d2. Remember the Black-Scholes formula, d1 we said log s by k plus r plus sigma squared by 2 times t divided by sigma root t, and d2 we said d1 minus sigma root t. So that would have become log s by k minus of r plus sigma squared by 2 times t by sigma root t. So that's where we are getting minus d2, right? So z greater than or equal to minus d2 is something that we are getting. So what does that mean? I can very well say now the price, so the call options the value is maximum of st minus k. Now what is st here? St I can very well find out, which is s naught into e to the power of r minus q minus sigma squared by 2 times t plus sigma root t does z. This is st minus k comma 0, and this will come only when z is greater than or equal to minus d2. So what I can very well do now is, so once I know z, which is a standard normal equation, standard normal variable, so I can very well start finding out. I know that the density function for a standard normal variable is 1 by root 2 pi e power minus half x squared, and from there I can very well find out if I want z greater than or equal to minus d2. It's as good as taking the integral of z from d2 to infinite e to the power 1 by root 2 pi e to the power of minus half x squared dx. But here the scenario comes is I want to integrate st minus k. So that's where I will take the same logic. This will continue 1 by root 2 pi minus d2 to infinite. So what is st? S naught into e to the power of r minus q minus sigma squared by 2 into t plus sigma root t into x minus k, because here I am taking x as z. With respect to z I am doing this integration. So that's the reason I am taking this e to the power of minus half x square dx, and I need the present value, so I will take e to the power of minus rt. Now I will try to break these two terms separately, right? So the first term will become s naught by root 2 pi into integral of minus d2 to infinite e power minus rt, e power plus rt gets go off. So it becomes e power minus qt, e power minus qt, and this is becoming minus sigma squared by 2 into t plus sigma root t times x. This is what it is. Minus sigma squared by 2 into t plus sigma root t into x minus even multiplying this with minus x squared by 2, so it becomes minus x squared by 2, minus x squared by 2. And this, the second term, I am taking it as k by root 2 pi e to the power of minus rt, right, e to the power of minus rt, and integral minus d2 to infinite e to the power of minus x square by 2 dx. So separately I am taking both of them. So here qt is a constant, so I can take it as s naught e to the power of minus qt divided by root 2 pi into e to the power of minus d2 to infinite. This I can very well write it as, I am taking out minus half. So sigma square t plus half sigma root t times x minus x squared by minus half plus x squared. So it is typically becoming x minus sigma root t whole square. Just write out x squared by 2 and minus 2x sigma root t, 2 by 2, so x sigma root t plus sigma squared t by 2. So I can write this something like this: dx e to the power of minus half x minus sigma root t whole square dx minus k by root 2 pi e to the power of minus rt, this minus d2 to infinite minus half x squared by 2 dx. Now frankly speaking, this part, if you look at it, k 1 by root 2 pi 1 by root 2 pi into minus d2 to infinite minus half x squared, I can very well write it as k e power minus rt and d2. Right, because 1 minus d2 to infinite minus half x squared by 2, this entire thing is directly working out to n d2. Whereas what about this one? Now x minus sigma root t, I'll take it as y. So dx will become dy. But on the other side, because this minus d2 if I am looking at, so y will take the values from minus d2 minus sigma root t. Otherwise it is becoming minus of d2 plus sigma root t, which is becoming minus d1. So what could have very well happened is the first part s naught by root 2 pi e to the power of minus qt integrated between minus d1 to infinite e to the power of minus half y square dy. So this is again s naught into e power minus qt minus d1 to infinite is nothing but n of minus d1, right? Minus d1 to infinite is nothing but from our minus infinity to d1, both are one and same, so that's where I can very well write it as n of d1. So the first part is becoming s naught into e power minus qt n of d1. The second part is becoming k e power minus t n of d2. That is what is the typical formula for Black-Scholes equation, which is directly coming out for the pricing of the call option. So this is a mechanism that is typically engaged. Once I know the log normal model for evaluating the asset prices, wherein the relationship is logarithm of st by st1 is mu minus q minus sigma squared by 2 times t2 minus t1 plus sigma square root of t2 minus t1 times z. Once I have established that equation, I can solve the price of the call option or a put option, especially the European option, just by looking at their payoffs, finding out the expected value of the payoff, and then finding out the present value of the expected value of the payoff. So this is what is the typical mechanism to solve the equation and arrive at the Black-Scholes formula through a risk neutral evaluation model. All right. Now let's look at the value of an option with this kind of a payoff. So probably if I am assuming to start with square root of st is some p, I can very well write this as value at time t is maximum of k minus pt. P is nothing but the price. I mean square root of st is what I am calling as pt. So it is becoming a maximum of k minus pt comma 0. So it looks more and more like a put option. As per the Black-Scholes framework, I know that the price of the put option, the value of the put option is directly coming out, because this is behaving more and more like a put option only for me. So from this particular framework, I can very well get that the value of the put option is k e power minus rt n of minus d2 minus s naught e power minus qt n of minus d1. So going with that kind of a framework, here instead of S naught, I will call it as P naught. So the value of this put option will come out as K e power minus RT n of minus D2 minus P naught e power minus QT n of minus D1. Now P naught is nothing but square root of S naught, right? So I can very well write it as e power minus rt n of minus d2 minus square root of s naught e power minus qt n of minus d1. That is the typical value that can come out for a put option on the maturity date. Or probably even if I have to go for a derivation for the same. So directly if I am using the Black-Scholes model, this is what that I am going to get. But otherwise, if I am directly going with the derivation using the log normal kind of a framework, I am writing it as k minus pt comma 0. Pt is what I am directly assuming it as square root of st. So I am directly taking the pt. So which means if I want to find the value of the call option at time 0, I am taking it as e power rt, the expected value of vt. So it's as good as saying e power minus rt times the expected value of maximum value of k minus pt comma 0. And typically this will occur when k is greater than pt. Only when k is greater than pt. So now the other expression that I want is p, when I am looking at log pt by p0, I can very well write it as, I can very well risk neutral pricing mechanism, the log pt by p0, I can very well write it as r minus q minus sigma squared by 2 times t plus sigma root t times z. So from here I can get pt equal to p naught times e to the power of p naught into e to the power of r minus q minus sigma squared by 2 times t plus sigma root t times z. That is coming out to pt. So my interval is when k is greater than P naught into e power r minus q minus sigma squared by 2 times t plus sigma root t times z, I find that the payoff will be k minus pt. So other way of saying is this is less than k. Right, whenever I am saying this is less than k, or the other way is saying z is less than log k by p naught minus r minus q minus sigma squared by 2 into t divided by sigma root t, z less than this number. So it is also being said that z less than, if I am taking a minus out, I can write it as log p naught by k plus r minus q minus sigma squared by 2 times t divided by sigma root t, which is coming out as z less than minus d2. It is coming out as r minus q minus sigma squared by 2 into t is directly coming out as z less than minus d2. So when z is less than minus d2, I see that the payoff is k minus pt. So now I'll go ahead in terms of finding the integration during. So what is the price of my put option with what is the price of my put option there? I'll take it as e power minus rt divided by square root of 2 pi. I'm trying to integrate it z less than minus d2. So minus infinity to minus d2 is what I'm taking. Z less than minus d2. So I'm taking minus infinity to minus d2. I'm taking p0 e power r minus q minus sigma squared by 2 into t plus sigma root t into x, right? So I want k minus pt. So that is the expected value. So I'll do it as k minus this. And what is the what is the equation for a standard normal variable z? It is e power minus half x square dx. So probably I could very well write it as e power minus rt by root 2 pi into k into integral of e to the power of minus infinite to minus d2 e power minus half x square dx, and probably let me expand the remaining part. So e power minus rt and this is e power plus rt going off. So directly I can say 1 by root 2 pi integral minus infinity to minus d2. So I'll get it as e power minus qt, right, e power minus qt minus sigma squared by 2t minus half x squared plus sigma root t x dx. Now probably if I am looking at this part, right, let me look at this part wherein it is coming out to 1 by root 2 pi, looking at minus infinity to minus d2 root t sigma root tx whereas x squared sigma squared by 2 into t. So I take out e power minus qt. Let me take out e power minus qt. Otherwise it is becoming e to the power of x x x minus, if I take even half out, it is becoming x minus sigma root t, x minus sigma root t whole square dx. So it is becoming x minus sigma root t whole square dx. So I could very well now look at the first part. Typically is k e power minus rt by square root of 2 pi. I am integrating it between minus infinity to minus d2 e to the power of minus half x squared dx. Now probably here if I say x minus sigma root t, if I am taking it as y, then dx is coming out as dy. And when I am looking at substituting, instead of x I am taking, let's say y, instead if I have to translate it into y, it becomes minus d2 minus sigma root t equal to y, minus of d2 plus sigma root t equal to y, and this is what becomes minus d1. So this is actually becoming e power minus qt divided by root 2 pi into minus infinity to minus d1, minus infinity to minus d1 e power minus half y square dy. So this entire thing is becoming nd1, right? This entire thing is becoming nd1. So I am getting e power minus qt by root 2 pi times n of d1. And what about this? This is coming out to n of minus d1, because it is up to minus d1, and this is coming out k e power minus rt by root 2 pi n of minus d2. So directly it is working out to the formula k e power minus rt by root 2 pi n of minus d2, and I am also looking at p naught e power minus qt by root 2 pi n of minus d1, and p naught is nothing but square root of s0. Instead of p naught, I will write it as square root of s0 e power minus qt divided by square root of 2 pi n of minus d1. So just like a typical Black-Scholes framework, wherever we had st, I will take it as square root of st. That's the only thing, and that is what will give me the value of the corresponding option. So just like a Black-Scholes formula, just like the pricing of the Black-Scholes formula, instead of st, I am substituting square root of st. Or similarly, instead of s0, I am substituting square root of s0. That's the only process that has gone into this calculation, right? Let's try to look at finding the price of an option using the Black-Scholes formula, but using two different kinds of mechanisms to compute the cumulative normal distribution value. Right, to compute the cumulative normal distribution value, let's say let me depend on two different kinds of mechanisms, and then try to compute the value of the call option using the Black-Scholes formula. So we are talking about a 3-month ATM call option, Okay, so let me try to enter a few details regarding the same. Strike price is 40, the spot price is 40. So S I will take as 40. The K, which is the strike price, I'll take it as 40. The time to maturity T, I'll take it as 3 months, which is 0.25 years to maturity. And the spot price is following a log normal distribution. Volatility sigma. The volatility sigma is being taken as 20%. It's paying dividend continuously at the rate of 1%. So I can take Q, which is a continuous rate of dividend. I'll take it at 1%. And risk-free rate of return, I'll take it at a constant 5%. Fair enough. Now, from this, probably I can compute first of all the D1. Going with the basic formula for normal distribution, for the Black-Scholes formula, I can remember that the formula of D1 is nothing but log S by K plus R minus Q plus R minus Q plus sigma squared by 2 into T divided by sigma root T. And D2 will become D1 minus sigma root T. So I can first find out the D1 and D2 using this mechanism. So I'll take it as log S by K plus R minus Q plus sigma squared by 2 multiplied by T divided by sigma root T. So this is sigma into square root of T, right? So this happens to be the value of D1, and D2 comes as D1 minus sigma into square root of T. So D2 comes to 0.05. Now I need to compute the cumulative normal distribution of D1, which is N of D1 and N of D2, because if we remember, the formula for a European call option as per the Black-Scholes formula is S naught e power minus qt n d1 minus k e power minus rt n d2. So this is what is the Black-Scholes formula. So S naught is known, e power minus qt, k e power minus rt. All I have is unknowns is n of d1 and n of d2. So for that, I have to compute this n of d1 and n of d2 going with different kinds of routines, different kinds of mechanisms. So one such routine is presented to us here, and it says using this try finding out the value of the cumulative normal distribution. Okay, let's try it out, but directly if I am using the spreadsheet formula, I'll use it as norms dist, where I give this as a value with a cumulative, saying that I should get a value 0.55 here, and for ND2 I should get 0.51. But yes, let's try out using the numerical methods that are available with us. Try finding out what is the value of ND1 and ND2 that I have got. Okay, so let me progress first with the routine that has been provided. So I'll take D1. In this case, my D1 is 0.15, D2 is 0.05. right? Okay. So for D1, first let me do it with respect to D1 so that I'll compute ND1. I'll start with D1, which is 0.15. So Z, going with this, we'll go step by step. Z is absolute value of T. So Z comes out to be the absolute value of T. Okay, this is what is Z. Then Y, which is coming out in this routine, 1 by 1 plus this much number times Z. So 1 divided by 1 plus 0.2316419 times Z. 0.2316419 times the Z. So this is what has worked out to be the value of Y. After that they have given some constants. A1 is specified as constant 0.3193 81530. 0.319381 that is the value of A1. A2 is coming out as minus 0.3565 minus 0.3565 63782. A3 is getting worked out as 1.7814 77937. A4 in the routine is working out as minus 1.8212 55978. So this is a kind of a routine that has been written to typically compute the value of the cumulative distribution of cumulative normal distribution of any particular number. Let's write out A5 1.3302 74429. So these are the numbers that have been specified. So they are like constants. Then we are saying M. We are calculating the value of M. 1 minus e to the power of t squared by 2 times a1y plus a2y squared plus a3y cube plus a4y power 4, something like that. So I'll write it as 1 minus e to the power of minus t squared by 2. So I'll write it as minus 1 times t. T is nothing but my d1. T squared by 2. E to the power of minus t squared by 2 multiplied by a1y plus a2y squared, something like that. So a1 times y plus a2 times y squared plus a3 times y cube plus a4 times y to the power of 4 plus a5 times y to the power of 5. This entire thing divided by square root of 2 pi. So square root of 2 times pi. When I am doing this entire exercise, I got my M as 0.559618. So I am taking this 0.559618, which I have got even through this mechanism as well. So that's this is one way out to typically use my different numerical methods to find out my n of d1. So basically my n of d1 through this mechanism is going to work out to this particular value. Same way I can try finding out n of d2 as well. So what I'll do is to find out n of d2 through this, I'm just copying the stuff. The only difference being instead of d1 being pointed to something, I'm taking my d1 as or probably D2. So I'll call this as D2. The rest all should be fine. I've got my value as 0.519939. That is what I've got earlier also. So my n of D2 becomes this number. Now that I know that these are my n of D1 and n of D2, I can find the price of the call option. So through this routine, the price of the call option is coming out as the spot price multiplied by e power minus qt e power minus qt multiplied by n of d1, which is coming through this routine, minus the present value of the strike price k times e power minus rt multiplied by nd2. nd2 coming out of this routine is working out to this particular number. So the price of call option going with this kind of a mechanism is working out to 1.789613. Probably the same logic if I am applying here directly using the Excel based formula. Let me try out. What is the price of this call option? S naught times e power minus qt times nd1 minus the present value k times e power minus rt times nd2. So this is giving me the price of call option SEP 1.789615. This has given it 789613. So there's a small change between the two methods, probably at the 6th decimal after the decimal point. That is where the difference is typically coming up. Right? Now, the same logic I can very well rely on. Now I am asked, compute the same Black-Scholes formula of the call using the Simpson's rule with a tolerance of 10 to the power of minus 12. So again, using the Simpson's rule, if I have to compute both for D1 as well as D2, so let me do, let's say 128 sub-intervals, because we can execute that in Excel very quite comfortably. So I'll go with the Simpson's rule, probably with 128 intervals. So my A goes like 0, B goes with whatever is my D1 value. So I'm taking the D1 first of all, this as my D1. The number of intervals, I'll take it as 128, which means the size of each of the interval for me is B minus A divided by N. So using this, I am getting the size of each of the intervals, let's say is something like this. So based on this, I am starting off A0, A1, something like that. So probably I am saying right from 0 to 1, I am taking my routine until 128. So this is my routine going until 128. So A0 is like a 0. But from the next one onwards, I am incrementing this with the H value. So this is becoming my A1, and from there it is going on to A2, 128, which should become 0.15, which is the B. Alright, so that is one more input. So this is called A0, A1, A2. From there I also need my X. So from here I'll get the X, which is the average of A0 and A1 becomes X1. So an minus 1 and an, the average of those two is giving me the xn. So these are my x0 to x1, x2, so on kind of numbers, right? So we know that with respect to a normal distribution, the formula for the Simpson's rule is, or probably the integral formula is nothing but integral of 0 to infinite, if I am looking at, or minus infinite to infinite, e power minus x squared by 2 dx. So the density function, I know that it is 1 by square root of 2 pi e to the power of minus half x squared. So what I can very well do is I can find out this e to the power of minus half x squared for each f of the a's and f of x's. So what I'll do is, when I want f of a, I'll try to find out e to the power of minus 1 times x squared by 2, which is a squared by 2. This is giving me e to the power of minus x squared by 2. So I am finding out f of a's. I can also find out f of x like that, which from here comes out e to the power of minus 1 times x squared by 2. So this number comes out to f of x, right, e to the power of minus x squared by 2, coming out to this much. And from here I can very well find out my integral value. Integral value, if you remember that the calculation is 0.5. The calculation for this from the Simpson's rule, I try to find it out as 0.5 plus 1 by square root of 2 pi times f of a0 plus f of an plus twice summation of a1 to an minus 1 f of plus 4 times the summation of f of x1 to f of xn, and this entire thing multiplied by h by 6. So that is what is the typical formula for with respect to the continuous cumulative normal distribution function. So the same logic I'll try to apply. 0.5 plus 1 by square root of 2 pi 1 by square root of 2 pi multiplied by f of a0 plus f of an plus 2 times the summation of f of a1 to f of an minus 1. So all these plus 4 times the summation of f of x1 to xn. All these summations need to be multiplied by h and divided by 6. H and divide by 6. So this gives me the integral again 0.559618. 9618 coming out even through this Simpson's rule. So this is the number that is getting worked out through the Simpson's rule when I am going ahead with finding out n of d1. So this is what is my n of d1 as per the Simpson's rule. And just to simplify my scenario, what I'll do is even for n of d2, I'll try to take it here itself. A is 0, B will come out to be my d2 value. So B comes out as the d2 value, I'll take it here. N is this much, H is this, fair enough. The integral value is coming out as 5.519,873. Let me just check, did I make any kind of a mistake? This is my H, A0, H1. So here it is coming out as A0, which is this one, plus whatever is the H. This is the H. So because of this, what is working out is all these numbers are getting updated. And here I am seeing that ND2 is 0.519939. So using this, probably I can very well compute the price of call option through this mechanism, wherein I am taking the spot price times e to the power of minus qt times nd1, nd1 obtained through the Simpson's rule, minus the present value of the strike k times e power minus rt times nd2 computed through the Simpson's rule. So this is giving me that the price of the call option is 1.789615. Even this mechanism is giving 1.789615. So probably just trying to increase the price even a little bit, probably going for 12 digits post the decimal point, right? In all the cases, I'm taking 12 digits post the decimal point, and probably even here when I'm looking at 12 digits post the decimal point, $1.789614929076. There is a small difference that is coming out here as well as here. So typically it is observed that the call option is getting priced even through Excel. When I am looking at the call option is getting priced more through this Simpson kind of a rule, because we are seeing that the price of the call option here is more or less matching the price of the call option here. The last 9076, the same kind of numbers are being represented. So that is where I could typically understand what kind of a mechanism is being absorbed. But in reality, I have two different rules. Either I can go with a Simpson rule, or I can go with this kind of a routine to compute my n of d1 and n of d2, and based on the computations for n of d1 and n of d2, I can very well do the pricing of my call option or put option using the Black-Scholes kind of formula. Alright, so this example should give a clarity. If I am looking at just to around 4 digits after the decimal or 5 digits after the decimal, my n of d1s would be more or less matching, but depending on the kind of a routine that is being used, the real difference between the n of d1 occurs, and that's where could result in the price of the call option also differing. But remember, it's not one call option we are going with. there could be a purchase of thousands of call options, which could very well result in a change in the overall profit or loss positions. So that's where there should be a deep lookout in terms of the significance level or probably the number of digits after the decimal point. The price has to be looked from. All right. Now let's understand these two key values that we compute during the Black-Scholes process. We first compute D1 going with log S by X, S by K plus R plus sigma squared by 2 times T divided by sigma root T, and D2 we take it as D1 minus sigma root T, or probably it is like this minus sigma root T comes out as log S by K plus R plus sigma squared by 2 into T minus, when I say sigma root T, it comes out as sigma squared T divided by sigma root T. So that's where it comes out as log S by K plus R minus sigma squared by 2 into T divided by sigma root T. So this comes out as D1, D2, and we also compute ND1, which is the corresponding normally distributed value, standard normal distribution value associated with D1 and D2. This is what we typically compute, and after that we come to a conclusion that or we compute a computation that the price of a European call option goes as spot price into e power minus qt, which is the present value of the continuous dividend, nd1 minus the present value of the strike price into nd2. So this is what we give as the price of a call option. Now, what are these nd1 and nd2? What do they signify? So just before I go into that, let me try to take one simple example, right, where I want to compute what is the probability that the option expires in the money. European option, what is the probability that the option expires in the money, right? So let's try to compute that. When I say probability that the option expires in the money, the spot price on the maturity date at time t should be greater than the strike price in case of call. Probability that the spot price should be less than the strike price in case of put. Correct? Now, we know that for a call option where we are looking at the underlying asset under the assumption that it is following a log normal distribution with parameters mu and sigma squared, where mu is the mean of the underlying normal distribution, sigma squared is the variance of the underlying normal distribution. We know that the log normal distribution is coming out this way as logarithm of st2 divided by st1. I can express it as mu minus q minus sigma squared by 2 into T2 minus T1 plus sigma square root of T2 minus T1 times Z, because any normally distributed nor random variable can be written in the form of mu plus sigma Z, where mu is the mean and sigma is the standard deviation of that normal random variable. And we have seen that logarithm of st2 by st1 can be expressed in this kind of a form. Now, when I am going with this logic, if I have to talk about the same t and We are talking about 0 and t. So when I take these two things as 0 and t, I can very well write it as log of st by s0 is nothing but mu minus q minus sigma squared by 2 times t plus sigma root t times z. Now for me, I require the probability that st is greater than k in case of call. So what I can write it is the probability that st by s0 is greater than k by s0. I can very well write I am dividing both of them by s0. Probability of st by s0 greater than k by s0, which is in other way st by s0. I know that this is the case, so I'll write it as probability of mu minus q minus sigma squared by 2 times t plus sigma root t times z greater than k by s0. I can very well write that. Now, so this is log st by s0. I cannot write st by s0 in that particular form. It is log st by s0 is this one. So when I am taking st by s0, I am looking at it as probably I could very well write even in case of log st by, so I could take the logarithm on both sides. So I want probability of log st by s0 greater than log k by s0. If that's the case, I can say log st by s0 greater than log k by s0. That is what I may have to write here. Now, okay, let me write it again. Probability of, I need to find the probability of mu minus q minus sigma squared by 2 times t plus sigma root t times z is greater than log k by s0. This is what I need to find. Now from here I will try to find what is the probability of z greater than. So I'll go step by step. Z greater than, if I want, I'll take it as log k by s0 minus of mu minus q minus sigma squared by 2 times t divided by sigma root t. If you just imagine now, mu minus q, in case it is equal to r, in case the mu minus 2 is equal to r, it is coming out as probability that z is greater than log k by s naught minus r minus sigma squared by 2 into t divided by sigma root t, which is nothing but z greater than d2. Otherwise, it is z greater than some value a. So when I take z greater than a, I could find it. So in normal case, I can write that this is probability of z greater than a, or probably z less than or equal to a minus a. Probability of z greater than a is nothing but probability less than or equal to minus a, and then I could very well write it as n of minus a as well. But in case I am talking, so n of minus a is something which is a cumulative distribution of n of t that can be estimated from our tables. But whenever I am looking at the scenario, mu minus q is same as r, then it becoming probability of z greater than d2 or probability of z less than or equal to minus d2. Otherwise, it is becoming n of minus d2. Right? So the probability, so if I'm saying mu minus q, okay, so it is coming out probability of Z greater than D2, which is working out to N of minus D2. So the probability that the option expires in the money, call option, Z greater than D2. No, Z is greater than minus D2 here. Because if I am looking at mu minus q equal to r, I need log s naught by k, not k by s naught. So this is coming out as probability z greater than minus d2, otherwise it is less than or equal to d2. So it is becoming n of d2. So n of d2 is the probability that the call option will expire in the money only under the condition that mu minus q is working out to be equal to r. So when we are assuming that the underlying asset net its dividend is growing at the constant risk-free rate, then I can very well assume that the probability that the option will expire in the money for a call option is just n of d2. So n of d2 which we are using in the Black-Scholes formula model is nothing but the probability that the option will expire in the money in case of call option under the assumption that mu minus q is equal to r. The same way, earlier, if you remember, we have computed the delta of the call option, which we said e power minus qt n of d1. E power minus qt n of d1 is the delta of call option. If the q equal to 0, which means no dividends are declared, then we can say that delta of the call option is same as n of d1, that is coming from the Black-Scholes formula. So what we can very well say is the Black-Scholes formula, whatever nd1 we are getting, in case of a call option, it is the same as delta if the underlying asset does not pay any kind of a dividend. But if it pays a dividend, then the delta is not the same as the ND1, because delta becomes the present value of ND1, because I mean adjusted with the present value of the dividend factor e power minus qt times ND1. So only when the dividends are not declared, I can take it as the as the delta of the call. ND1 is same as the delta of the call. But when I look at ND2, I am simply here talking about risk neutral probability. Risk neutral probability that the option will expire in the money. Why risk neutral? Because if you remember, we have made an assumption that mu minus q should become equal to r. R is a risk-free rate. So whenever that risk neutral probability is being replacing this mu minus q, then only we are saying nd2, whatever is the term in the Black-Scholes formula, that will indicate the option, the probability that the option is expiring in the money. So those are the two interpretations of ND1 and ND2. Even if the underlying asset pays a dividend or does not pay a dividend, there it doesn't matter. The option is expiring in the money. ND2 I am calling as option expiring in the money only under a risk neutral probability scenario. And when it comes to put options, if we see that we have identified the delta of the put option as minus e power minus qt times n of minus d1. Again, the same logic, if the underlying asset does not pay any dividend, the delta is minus n of minus d1 or minus of 1 minus nd1 or otherwise n of d1 minus 1. So this is the delta only in case the dividend are not paid by the underlying option. Similarly, when I am looking at n of minus d2, we are talking of risk neutral probability that the put option expires in the money. And simple way for us to understand is when the call, see when I am talking of ND2, we said that the probability that the call option expires in the money. So when the call option expires in the money, it is the probability that the corresponding put will expire out of money. So for the put to expire in the money, I have to take it as 1 minus the probability that the put will expire out of money. So which is nothing but n of minus d2. So n of minus d2 is the probability that the put will expire in the money. N of d2 is the probability that the call will expire in the money. So an understanding of ND1 and ND2 will be required from this particular dimension to typically have a hold on assessing the delta or computing the probability that the call will expire in the money, out of money, put will expire in the money, out of money. So the conceptual aspect with respect to the Black-Scholes formula should be required from this dimension to really price and evaluate the derivatives in a more objective manner. Alright. Let's try to understand from a basic numerical as to how do I really differentiate between ND1 and delta. Sometimes we talk about in case of a call option, whenever we use the formula delta of a call option, we say ND1 is the delta. Similarly, when I talk about ND2, we say that this is the probability that the option expires in the money. So, when do we say that they are equal? When do we say they are different? Let's try to compute and try to understand the difference very clearly. Consider a 5-month European call option, strike price 45, spot price 50. So spot price is 50, the strike price is 45, 5 months, the time to maturity is 5 by 12 years, following a log normal distribution with a drift of 3%. So mu, or probably let me call it u, the mu which is the drift coefficient that we are saying is 3%. Then volatility sigma is being looked at as 30%. Paying a dividend continuously, Q is coming out as 1%, and the risk-free rate of return is being taken as 3%. Now, from here, if I have to compute ND1 to start with, right, if I am computing ND1, all I am going ahead with is log S by K plus R minus Q plus sigma squared by 2 times T, or sigma squared by 2 times T divided by sigma root T divided by sigma root T. That is what we call as ND1, not ND1, D1. That is what we call as D1, and D2 is nothing but D1 minus sigma root T, sigma into square root of T. So this is what is D1 and D2, and from here I am getting ND1, which is the norms distribution associated with this particular value, norms distribution associated with this particular value, giving me 75.29%, Similarly, if I am looking at ND2, the same logic is working out to 68.8%. Now, so the ND1 is this particular number, but when I look at delta, let's understand the formula for delta is e power minus qt times ND1. So which means it is equal to ND1 only when the asset is non-dividend paying. When the asset is dividend paying, I'll get the delta as e power minus qt times ND1, or the present, ND1 discounted by e power qt, or discounted by e power multiplied by e power minus qt. So my ND1 could be a slightly lesser, my ND1 could be a slightly higher value compared to delta, especially if the stock is a dividend paying kind of a stock, the asset. So typically whenever I talk about ND1 from a Black-Scholes formula for a call option, when I say I am trying to equate it to delta, then the underlying scenario is whatever is the underlying asset that does not pay dividend. But if it is paying dividend, I will typically see that the ND1 will not be the same as that of delta. ND1 will be slightly more than that of delta, which has been observed in this case also. ND1 is this much, the delta is this much. So that's one difference that we can clearly understand. Now, ND2. In this case, I have computed the ND2 as 0.688035, so 68.8%. But in case of a call, the other computation which we talk of is the probability that a call option expires in the money. So whenever we are talking of probability that a call option is expiring in the money, we are saying we want to find out the probability that ST is greater than K. So when we are looking at probability of ST is greater than K, I am looking at a simple logic. So probably let me go ahead with basic understanding. Log ST by S0. Right, log ST by S0, we can write it as mu minus Q minus sigma squared by 2 times T plus sigma root T times Z. Very straightforward. So this is the basic logic. So if I want probability of ST greater than K, it's as good as saying probability of ST by S0 greater than K by S0. Right, and from here I can get ST by S0. I can or probably it can be written as probability of log ST by S0 greater than log K by S0. Fair enough. Log ST by S0, I am directly substituting mu minus Q minus sigma squared by 2 times T plus sigma root T times Z greater than log K by S0. So from here I can very well come out saying Z greater than log K by S0 minus of mu minus Q minus sigma squared by 2 into T divided by sigma root T. So I want to find out what is the probability of Z greater than this much. Right, mu minus Q minus sigma squared by 2 into T log K by S naught minus mu minus Q minus sigma squared by 2 into T divided by sigma root T. So that's where we'll try to find out the RHS value if I find out, that is what is coming out, Z value greater than that much. So I want to find out what is the probability that the Z value is greater than that much, or Z value is lesser than minus of that much, right? So in this case, let me go log K by S naught, log K by S naught minus mu minus Q minus sigma squared by 2 times T divided by sigma root T. Sigma root T. So RHS is completely minus 0.49. So I need a value Z greater than minus 0.49, or so I need a value Z, probability of Z greater than minus 0.49, or the other way of saying is probability of Z lesser than the minus of minus 0.49, Z lesser than 0.49. So that's where I will get the n of d2, or probably if I want probability of Z less than minus 0.49 is coming out as, I can take the norms distribution, this particular value 1. So overall telling me norms distribution probability of Z less than or equal to, or the minus of this. So that's where I'm taking it as 0.688. So which means in this case, this came equal to ND2. The reason why these two came equal for me is the R and the mu are the same. When the R and the mu are same, we'll find that ND2 is same as the probability that the stock will expire in the money. But otherwise, probably let me just change this mu to 4%. What I'll find is ND2 will still be 0.688, but the probability that the stock will close in the money is 69.56 higher. In case the mu is lesser, I find that ND2 is still the same, but the probability that the stock will close in the money is going to be much lesser. Only in the scenario where mu is equal to R, ND2 as well as the probability that the call option expires in the money, both of them are one and the same. So just to summarize the scenario, whenever I'm going ahead with the risk neutral probability, the call option expires in the money goes as ND2 when I'm looking at mu equal to R. Whereas when I'm looking at any other difference between the mu and R, mu equal to R is I'm going with a risk neutral valuation itself. Whenever mu is equal to R, I say that the probability that the call option expires in the money is same as ND2. Similarly, when I say ND1 is same as delta, the underlying assumption is that particular underlying asset is not going to give any kind of dividend during that option expiry period. This is what we need to understand before we directly use ND1 as a representation of delta and ND2 as a representation of the probability of the call option expiring in the money. Alright. Now let's look at some of the analysis with respect to a Black-Scholes formula. Especially we'll see how the how the price of a call option or a put option, price of a call or put get affected with respect to time to maturity. What is happening as the time to maturity goes larger and larger? So probably the better thing is always look out for a small example. So let me create a simple Black-Scholes scenario by taking some current stock price, the strike price K, the risk-free rate of return, the volatility, which is sigma, and finally the time to maturity. So let me assume that the current stock price is 100, the strike price is also 100. Let's say the risk-free rate is some 6%, the volatility is around 25%, and let's say we are talking about a 3-month option. Okay, just for taking some numbers, I have taken some of them. Now based on this, we can compute D1, which goes like log S by K plus R plus sigma squared by 2, this entire thing multiplied by T, R plus sigma squared by 2 multiplied by T divided by sigma root T. So sigma square root of T. So this is coming out as the D1, and in this case the D2 is coming out as the D1 minus sigma into square root of T, that is the value of D2, and from here I can find ND1, where I can take the norm distribution with respect to this. So ND1 is coming out to 0.57, and similarly I can find out ND2. The ND2 also is coming out. ND2 is coming out to 0.52. From here I can find out the price of the call option, the spot price multiplied by ND1 minus the present value of the strike price. So this divided by e power RT times ND2. So this is the price of the call option here. And what about the put option? I can use the call put parity relationship. Call put parity is saying C minus P is equal to S minus K by e power RT. So from here I can very well find out P, C minus S plus K by e power RT. So it comes out as C minus S plus K by e power RT. Okay, fair enough. Once I have a framework in place, let's play out all the situations. So here the question is, what are the values of the following plain vanilla European options as the time to maturity goes to infinite? So I want to increase the time to maturity. Right now we have just taken time to maturity is 0.25 years, very small. But what these are saying is, as the time to maturity goes to infinite, what is going to happen for at the money call, at the money put? First of all, here it is at the money only because the spot price and the strike price are more or less the same. So right now I am seeing that these are the call and put. So what I'll do is, we'll try to use different kinds of possibilities for the time to maturity. So the time to maturity instead of 0.25, let's say I will increase it to 0.5, 1, 2, 3, 5, 10, 20. This is where we talk about going closer to infinite. So if these are the possibilities of time to maturity, I want to find out what is the price of the call option. So I want to find out what is the price of the call option in all these cases. So I'll use a simple what if analysis called a data table and just try to check out that I want to find out by replacing it here what is the price of the call. So what we are seeing is the price of the call is almost approaching the spot price as we are increasing the time to maturity. As the time to mature, so what is the relationship here? As the time to maturity goes to infinite, what I could see is the price of the call is approaching the spot price. The price of the call is approaching the spot price. And what about the case of put? Instead of observing the call, I want to observe the put. So in this case, what is happening is as the time to maturity is increasing, as the time to maturity is increasing, I am seeing that up to a certain point in time, the put has, see here we are seeing that up to a certain point in time, the put has gone up in value, but after that slowly it is falling towards 0. Right, up to a certain point in time, the value of the put has really gone up. And what we have seen is after a certain point, probably up to 5 years or 10 years, up to 3 years, the value of the put has typically gone up. And after a certain point in time, I am seeing that the value is dropping. So that's another scenario that I could see just with an at the money call. If I look at tracking the at the money call, I could see that as the time to maturity is increasing, the value of the call is approaching the value of the spot price. But in case of at the money put, put, what we are observing is up to a certain time to maturity, we are seeing that the value of the put is increasing, but beyond that, we see that the value of the put is falling, and as it is approaching infinite, we are seeing that the value of the put is going to 0 itself. So probably the moment it is tending to infinite, we are seeing that the value of the put is going closer and closer to 0. Then 10% in the money call. So whenever we are saying in the money, the spot price is greater than the strike price. So probably here I am looking at the spot price is 10% more than the strike price. This is where I am talking about 10% in the money call. So let's see what happens in case of 10% in the money put also. Even there, what is that we are observing is up to a certain number of years, we are seeing in case of puts, that is what we are observing. For a certain number of years, the value of the put is increasing, but beyond that certain time period, we are seeing that the value of the put is actually decreasing and it is approaching 0. So that is what happens. I'm more interested in 10% in the money call, but this is 10% out of money put. In case of 10% out of money put, in case of 10% out of money put also, we are seeing a pattern that up to some time the value of the put is increasing, and after that it is typically falling down to 0. Whereas when I look at 10% in the money call, I am looking at 10% in the money call. Even in that case, as the time to maturity is going to infinite, it is approaching the spot price. Right? So in the money call, we are talking about the approach is with the spot price as the time to maturity goes to infinite. Whereas in case of put, we are observing a pattern that something is going up and after that it is coming down. The same logic, probably if I am taking the spot price as 90, then this is 10% out of money call and probably 10% in the money put. This is 10% in the money put and 10% out of money call. So even in case of call, 10% out of money call also, I am seeing that the price is approaching the spot price. And similarly, when I am tracking the 10% in the money put also, I am seeing that up to a certain point, let's say up to 5 years, I am seeing that the value between 3 to 5 years, the value of the put is increasing. But beyond that it is slowly falling, and as the time to maturity is reaching infinite, the value of the put is going closer to 0. So just as a simple summary, we look at as the time to maturity goes to infinite, in case of a call, the value of the call option typically approaches the spot price, whereas in case of a put, it increases up to a certain period and after that gradually falls to 0. So it approaches the 0 as the time to maturity goes to infinite. So easier way for us to analyze from this kind of a tabular or from this kind of example based approach, all these kinds of relationships can quite comfortably be understood and evaluated. So this is a simplified summary to address, though in reality we talk about as the time to maturity increases, the price of the call option also increases as well as the price of the put option increases. But a good understanding that we have got is, in case of call, yes, it increases and it goes up to the spot price. But in case of a put, it increases only up to a certain period. And after that, I see that the price of the put is gradually going down and finally touching 0 as we are seeing that the put option is going closer to, as the time to maturity is going closer to infinite. Alright, this is an excellent understanding that we can get in the behaviors of the call and put with respect to time to maturity. Let me try to get into the valuation of different types of options, not the traditional European or American kind of options. So let's try to see how we get into the evaluation of them using the risk neutral mechanism. Always remember, whenever I rely on this concept of risk neutral, I am talking about the present value, which means discounting by e power rt, the expected value of that particular instrument on maturity. So take R as the risk-free rate of return, which is constant, maturity T, strike price K, underlying asset S T or S0 with a current price of S0 with a log normal distribution with the mu and volatility sigma. Right? With these kind of scenarios being there, all I am trying to look at is the evaluation of asset or nothing kind of a call. So in case of asset or nothing kind of a call, what is the payoff? The payoff is either the asset whose worth will be st in case st is greater than k, or it would be 0 otherwise. So this is the logic. Okay, so first of all I am trying to understand the value is st in case so this is what will become the value at time t. It could be either st when st is greater than k, or it is 0 otherwise. So now if I have to know when is st greater than k, now that I know that it is a log normal, I can use this expression log st by log s0. I can very well take it as r minus q minus sigma squared by 2 times t plus sigma root t times z. So in normal case when we are talking about mu separately, otherwise I could have taken, it comes out as mu minus q minus sigma squared by 2 times t plus sigma root t times z. So this is what will be the log st minus s0. So from here I get st is s0 times e to the power of mu minus q minus sigma squared by 2 times t plus sigma root t times z. This is st. So I would be integrating this st, right, because I need the expected value of vt, and this can happen only when st is greater than k. So when I am saying st is greater than k, it's as good as saying this value is greater than k. And the other way of putting it out is z is greater than log k by s0 minus of mu minus q minus sigma squared by 2 times t divided by sigma root t. So this is what we are defining z as. Z is greater than log k by s naught minus mu minus q minus sigma squared by 2 into t. In case I am assuming mu the same as r, in case I am assuming the mu the same as r, then it becomes z greater than whatever I am substituting log k by s naught. So otherwise if I take the minus out, it becomes log s naught by k plus mu minus q minus sigma squared by 2 times t divided by sigma root t. So it becomes z greater than minus d2. If at all my r is same as q, then it becomes z greater than minus d2. So all it works out is, if I want the price of the call option, I'll take it as e power minus rt divided by square root of 2 pi e to the power integration from minus d2 to infinite. I'm looking at s naught e to the power of here I am taking mu itself, let's say mu minus q minus sigma squared by 2 times t plus sigma root t times x into e to the power of minus half x squared dx. Now this is where, instead of probably if I had not taken d2, it would have been like probably sum minus a. Let me assume it as minus a. So it is more like z greater than, I would have got it as z greater than log k by s naught minus mu minus q minus sigma squared by 2 times t divided by sigma root t. So I would have integrated that z completely. I would have integrated that z completely from log k by s naught minus of mu minus q minus sigma squared by 2 times t divided by sigma root t, right? So from this to this, I am integrating this part. So let's see what is coming out. So if I am integrating this from, so this part, if I am taking it as sum a, so it is saying z greater than a, or it is as good as saying z less than or equal to minus a. So probably because we are talking of z less than or equal to minus a, I am integrating it between minus infinite to minus a. I am integrating it between minus infinite to minus a, this particular value. So it is coming out as S naught. Now S naught into e power minus RT, or S naught divided by root 2 pi, e power minus RT, if I am keeping it as it is, e power mu minus R times t into e power minus qt into e to the power of minus sigma squared by 2 into t plus sigma root t into x minus half x squared dx. So basically when I am doing it with respect to x, it is coming out as s naught by root 2 pi e power mu minus r minus q times t e to the power of, so this I am to integrate between minus infinite to minus a. So I will integrate between minus infinite to minus a. If I am looking at e to the power of minus half, I am taking out. So x squared minus 2 sigma root x plus sigma squared t. So it is coming out as x minus sigma root t whole squared dx. So this is again S naught by square root of 2 pi e power mu minus r minus q times t. If I am looking at this, probably if I say x minus sigma root t is equal to y, dx equal to dy, and when I substitute minus a, it becomes minus a minus sigma root t. So it is becoming minus of a plus sigma root t. Right? This is becoming minus of a plus sigma root t. So I am integrating it between minus infinity to minus of a plus sigma root t. It is becoming e power minus half y squared dy. So this is directly becoming n of minus a plus sigma root t. So this is becoming n of a plus sigma root t. A is coming out to be this much. So what is this? A log k by s naught minus mu minus q minus sigma squared by 2 times t by sigma root t. This is A plus sigma root t. So this becoming sigma squared t and minus sigma squared by 2t. So this becomes log k by s naught minus of mu minus q plus sigma squared by 2 into t by sigma root t. So this becomes another, right? So this is one more, which is coming out mu minus q plus sigma squared by 2 into t. So it is finally working out that the price of the call option. So this part is working out to that much, which is finally working out to s naught by root 2 pi e to the power of mu minus r minus q times n of minus of a plus sigma root t. And what we are simply saying is, this is the price of the call option if it is an asset or nothing kind of a call. So this is the price of the call option in case of asset or nothing kind of a call, because we are going to get a payoff of ST when ST is greater than K, otherwise we are going to get 0. So let me repeat the process again, just for an understanding purpose. If I am saying asset or nothing call, the payoff is going to be ST, which was asset is delivered, especially when ST is greater than K, 0 otherwise. So because this is the situation and we are talking about drift mu, volatility sigma, I am simply saying log st by s0 because it follows a log normal distribution. I am saying it is mu minus q minus sigma squared by 2 times t plus sigma root t z. So from here I get S naught ST directly as S naught into e to the power of mu minus q minus sigma squared by 2 times t plus sigma root t times z. This is ST. Now when I want to find out the value of the call option, I am doing it as e power minus RT divided by square root of 2 pi. Integrate whatever is the payoff. The payoff is S naught into e power mu minus q minus sigma squared by 2 into t plus sigma root t into z or x into e to the power of minus x squared by 2 dx. So this need to be integrated, but I need to know what are the limits. The limits are found out from st greater than k. When I say st is greater than k, so I am getting s naught into e power mu minus q minus sigma squared by 2 times t plus sigma root t z is greater than k. Otherwise it is working out that I am looking for z. Z greater than log k by s naught minus mu minus q minus sigma squared by 2 into t divided by sigma root t. And this entire thing, log k by s naught minus mu minus q minus sigma squared by 2 into t by sigma root t, I am calling it as a. So it is coming out as z greater than a. So which is saying z less than minus a. Z greater than A is nothing but Z less than minus A. So I am taking it as minus infinite to minus A. I am taking it as minus infinite to minus A, this much. So as a part of a simplification, it is becoming S naught into e power mu minus r minus q times t, and I am by square root of 2 pi, and integrated between minus infinity to minus a, which is working out as e power minus half sigma squared t plus sigma root tx minus half x squared dx. Now keeping this part aside, this is becoming e to the power of minus infinite to minus a, e power minus half into x minus root t times sigma whole square dx. So that's where when I take x minus sigma root t equal to y, dx becomes dy, and the integral, the limits will become minus a minus sigma root t, the other one. So I am integrating it between minus infinity to minus of a plus sigma root t, e power minus half y square dy. Now this is directly becoming n of minus of a plus sigma root t. Right, this is becoming n of minus of a plus sigma root t. So directly this is coming out as a solution. This is coming out to me as S naught e power mu minus r minus q times t by square root of 2 pi. Now, I don't need square root of 2 pi because this entire thing comes to n of. So it comes out as n of minus of a plus sigma root t. So the overall, the payoff in case of asset or nothing kind of a call goes as S naught into e power mu minus r minus q into t into n of minus of a plus sigma root t. Otherwise, probably if you look at it, if mu had been equal to r, it could have gone directly as S naught into e power minus qt, n of my a would have looked as good as a d2, n of minus of d2 plus sigma root t is coming out as d1. Right, so it is directly coming out as n of d1 directly. So it would have directly given me S naught e power minus qt n of d1. Whereas because I am having a mu and r separate, I am going to get this kind of an expression. Minus infinity to minus of this one is giving me an expression which is S naught into e power minus mu minus r minus q times t n of minus of a plus sigma root t. Right? So this is the way I can work out for asset or nothing call. Now when I am looking at delta for the same, if I have to compute the delta, I am discounting it by S. So probably it can very well come out as e power mu minus r minus q t. So let me take the expression now. After that we can look at the delta. So I have got the expression. Let me look at the expression first. if I look at the expression, I got the price of the call option S naught into e power mu minus r minus q times t n of minus of a plus sigma root t. Now what we are saying is I want the delta for this, dou c by dou s. So I'll take e power mu minus r minus q times t n of minus of a plus sigma root t. This is one term plus S naught e power mu minus r minus q times t n dash of minus of a plus sigma root t. And I find whatever the derivative of whatever a I have taken log s naught by k. Now this part will become equal to 0 when I am doing a derivative with respect to s. So which means it will end out as s naught into e power mu minus r minus q times t. So this is a delta for all or nothing kind of a call. Now when I am going with all or nothing kind of a put, again it's the same way. So I am saying my payoff is ST provided K is less than ST is K is greater than ST or ST is less than K. Otherwise it's exactly the same, which means I am still integrating the entire S naught into e power mu minus r minus sigma squared, sorry, mu minus q minus sigma squared by 2 into t plus sigma root t into x into e power minus half x square dx. This is integrated only where st is less than k. So st is nothing but s naught into e to the power of mu minus q minus sigma squared by 2 into t plus sigma root t into z. So this is less than k. So otherwise it is saying z less than log k by s naught minus e power mu minus q minus sigma squared by 2 into t divided by sigma root t. So I can very well assume that this is a. So z less than a is nothing but minus infinity to a is what is coming out. So minus infinity to a I am doing it. So basically it is coming out as s naught into e. So I can even take e power minus rt by square root of 2 pi. So it comes out as s naught into e power minus q minus r times t, and this is directly becoming integration between minus infinity to a e power minus half x minus sigma root t whole square dx. So again I am taking x as x minus sigma root t as y. So this becomes a minus sigma root t. So it becomes minus infinity to a minus sigma root t. This becomes e power minus half y square dy. So obviously this is becoming n of a minus sigma root t. This part is becoming n of a minus sigma root t. So s naught into mu minus q minus r times t into n of a minus sigma root t. Right, so that is what is coming out for asset or nothing kind of a put. But when we are looking at cash or nothing call with a cash payout of B, so it's the only thing that is coming out in that case is I am integrating, let's say, between minus infinite to A. All I am integrating is B times e to the power of minus half x square dx. So it is coming out as b times e to the power, so which is coming out as n of a. In case of put, it is directly coming out as b times n of a, where a is that log k by s naught minus mu minus q minus sigma squared by 2 times t by sigma root t. So this is how we can very well compute for both cash or nothing call, cash or nothing put, asset or nothing call, asset or nothing put, depending on whether mu is equal to r or mu is not equal to r. The complete Black-Scholes value, and after that doing a differentiation of that with respect to s is going to give me the deltas for those kind of options, right? Let's look at the kind of Black-Scholes formula that can be computed for a forward price. So basically what we can look at is we'll take for a typical spot price itself, the price of the call option goes as S naught e power minus qt and d1 minus ke power minus rt and d2. So this is the typical price of the call option, and of course I know that d1 in case of a call option is log s by k plus r minus q plus sigma squared by 2 times t divided by sigma root t, correct? And of course d2 goes as d1 minus sigma root t. So this is what we have been using. Now what we are saying is, if I am saying f is the spot price into e to the power of r minus q into t. So wherever I am having s, I'll replace it as f by e to the power of r minus q into t to simplify the stuff. So here the price of the call option directly goes as, instead of s, I'll write it as e f by e power r minus q into t, e power minus qt n of d1 minus k e power minus rt n of t2. So if I try to write the expansion of this, right, it is becoming f e power minus rt plus qt minus qt and d1 minus ke power minus rt and d2. So this is working out as f e power minus rt and d1 minus ke power minus rt and d2. Other way of writing is, if I am taking out ke power minus rt altogether, so it is becoming f by k times nd1 minus nd2. So that is what is the price of the call option coming out here, right? And probably what about the d1 now? Here we said log s by k. So in case of d1, instead of s, I'll write it as f e power minus rt, right? F e power minus of r minus q times t, right? Probably here log f is nothing but, sorry, log s naught is f e power minus of r minus q times t divided by k, log s naught by k plus r minus q plus sigma squared by 2 times t divided by sigma root t. So what I can write here, I'll take it as only log f by k, I take it here, plus log e power minus r minus q into t becomes minus R minus Q into T plus R minus Q into T plus sigma squared by 2 into T divided by sigma root T. So this and this go off, giving me log F by K plus sigma squared by 2 divided by sigma root T. So that's where I can expand it, saying log F by K divided by sigma root T, and probably this gets evaluated as sigma root T by 2. So this is where the D1 is coming up, and D2 obviously D1 minus sigma root T. So if I am doing a minus sigma root T here, it comes out as log F by K divided by sigma root T minus sigma root T by 2. So that's how I am getting the values of the call option and the put option using this kind of a mechanism. Now what are we saying? Values of the at the money forward call. So we are talking about at the money forward call and put options are equal uh, at the money forward is stuck at the forward price. So if the forward price is going to be K equal to F, which is working out to SE per minus R minus SE per R minus Q time T minus T. If the forward price is at this particular, then the call and the put are going to be the same itself, because the put option is going to work out with this kind of a formula. So if F is, as long as F is equal to K, right, when I am saying F is equal to K, so it is becoming, call option is becoming KE per minus RT times ND1 minus ND2. Whereas the put option is becoming KE per minus RT times N of D2 is 1 minus ND2 minus F and K are same. So N of minus D1 is 1 minus ND1. So it's again working out as N of D1 minus N of D2 only, which means in case the forward price is K is S into E power R minus Q times T, then what we are simply saying is the price of the call option as well as put option on that the price of the call as well as put option are going to be equal, and that value is going to be KE per minus RT times ND1 minus ND2. A simple approximation or simple derivation for this formula with respect to the Black-Scholes pricing is going to come out. Alright.